Good morning, Ma'am. Today I was assigned to report about Lagrange theorem. Lagrange theorem was given by Joseph Louis Lagrange. States that in group theory, for any finite group, say G, the order of subgroup H of group G is the divisor of the order of G. That is, order of G divides by order of H. The order of the group represents the number of elements. Lagrange theorem was one of the important theorems of abstract algebra. Lagrange theorem statement. Lagrange theorem states that the order of the subgroup H is the divisor of the order of the group G. This can be represented as number of elements in G is equal to number of elements in H. One must understand what a coset is before one can fully understand the Lagrange theorem. So let us understand what the coset is. So coset, when G is a finite group and H is a subgroup of G, given that G is an element of G, then small gh is equal to gh and small h, an element of the big H, will be the left coset of H in G with respect to the element of G. Big Hg is equal to Hg, small h, an element of H, is the right coset of H in G with respect to the element of G. So before we proceed to prove the Lagrange theorem, let's understand first the three lemmas. First lemma. If G is a finite group and H is its subgroup, then there is one-on-one correspondence between H and any coset of H. Second lemma. If G is a finite group and H is its subgroup, then the left coset relation G1 approximately G2 if and only if G1 is H equal to G2. H is an equivalence relation. The third lemma. Let S be a set and approximately be an equivalence relation on S. If A and B are two equivalence classes with A intersect B is equal to empty set, then A is equal to B. Now with the help of the above mentioned three lemmas, we can easily prove the Lagrange statement. So, proof of Lagrange theorem. If G is a finite group and H be any subgroup of the group G, then order of group G is divisible by order of subgroup H. So to prove the statement, let G be a group of order N and H be any subgroup of G of order M. So as you can see, M is less than N. Number of elements in subgroup H cannot be greater than the number of elements in the group of G. So M is less than N. So we have to prove the order of H. It should be divide the order of G. That is, M divides N. So H is equal to H1, H2, H3, so on and so forth, and then Hm. But H1 and H2 cannot be equal. So Hi is not equal to Hg. Because for all I and G is equal to 1, 2, 3, and so on and so forth. Yan. Let A element of G be any element. Consider AH is equal to AH1, AH2, and so on to AHM. Show that AH has exactly M distinct elements. So we will show this by using the contradiction method. As you can see, naa sa example sa kilid, no, makita na to. So if possible, we take that AH has not M elements. So AHI is equal to AHG. So as you can see, A to the power of negative 1 AH is equal to A to the power of negative AH, and we will multiply it by both sides. So we will get the EHI is equal to EHG. So ang nabilin is ang HI is equal to HG. But to our previous na slide kanina, the order of H is H1, H2, and so on, Hm. But Hi is not equal to Hg. So, sa example na to, it's contradict to our order of H. So, if a group has m distinct closet, then the group is equal to union of all closet. So, that is, AH has exactly m elements. That is, since G is a finite group, so G is equal to A1 H union A2H union A3H union and so on AKH. Since all are distinct, means AIH intersect AG, H is equal to empty. So I is not equal to G. So G is equal to order of A1H plus order of A2H plus order of 3H plus and so on order to AKH. So since we have already proved that coset has also exactly m order or m elements, so order A is equal to m plus m plus m and so on plus m key times. So the n now is equal to, so as we add the m plus m sa key times, so n is equal to key m. And m, so ang n is multiple of m. So m divides by n. So for example, you can see 15 is equal to 3 times 5, and 5 divides by 15. So after we sum up the key plus m, we have now the n is equal to key m. So again, this means that n is multiple of m, and that then the m divides by n. So m is order of H, and n is order of G. So this proves that order of G is equal to n, and order of H is in any subgroup of order m. So therefore, H is any subgroup and G is any group. This proves that order of H should be with order of G. So that is what the Lagrange theorem. That's all, Mom. Thank you.